Hi, I'm Eduardo Janicas, and I'm a solutions architect at AWS. I've been here for over 2.5 years, and I have a background in networking and operations. I'm going to talk about how AWS achieves static stability using availability zones. At Amazon, the services we build must meet extremely high availability targets. This means that we think carefully about the dependencies that our systems take. We design our systems to stay resilient even when those dependencies are impaired. In this talk, we're going to define a pattern that we use called static stability to achieve this level of resilience. We'll show you how you apply this concept to availability zones, which are a key infrastructure building block in AWS, and therefore they are a bedrock dependency on which all of our services are built. We will describe how we built Amazon Elastic Compute Cloud, or EC2, to be statically stable. Then, we're going to provide two statically stable example architectures that we found useful for building highly availability in regional systems on top of availability zones. And finally, we're going to go a bit deeper into some of the design philosophy behind Amazon EC2, including how it is architected to provide availability zone independence at the software level. In addition, we're going to discuss some of the trade-offs that come with building a service with this choice of architecture. But first, let's explore and understand the AWS cloud infrastructure. A region is a physical location in the world where we have multiple availability zones. Availability zones, or AZs, consist of one or more discrete data centers, each with redundant power, networking, and connectivity housed in separate facilities. Availability zones exist on isolated fault lines, floodplains, networks, and electrical grids to substantially reduce the chance of simultaneous failure. It provides the resilience of performing real-time data replication and the reliability of multiple physical locations. AWS has the largest global infrastructure footprint, with 25 regions, 80 availability zones with one or more data centers, and over 230 points of presence with 218 edge locations. And this footprint is constantly increasing at a significant rate. Each AWS region has multiple availability zones. Each availability zone has multiple physically separated data centers. Each region also has two independent, fully redundant transit centers that allow traffic to cross the AWS network, enabling regions to connect to the global network. Further, we don't use other backbone providers for AWS traffic once it hits our backbone. Now, each availability zone is a fully isolated partition of the AWS global infrastructure. This means that it is physically separate from any other availability zone by a meaningful distance, such as many kilometers. Each availability zone has its own power infrastructure. Thus, availability zones give customers the ability to operate production applications and databases that are more highly available, fault-tolerant, and scalable than it would be possible from a single data center. All availability zones are interconnected with high-bandwidth, low-latency networking over fully redundant, dedicated metro fiber. This provides high-throughput, low-latency networking between availability zones. When interacting with an AWS service that provisions cloud infrastructure instead of an Amazon Virtual Private Cloud, or VPC, many of these services require the caller to specify not only a region, but also an availability zone. The availability zone is often specified implicitly in a required subnet argument. For example, when launching an EC2 instance, provisioning an Amazon Relational Database or RDS database, or creating an Amazon Elastic Cache cluster. Although it's common to have multiple subnets in an availability zone, a single subnet lives entirely within an availability zone, and so by providing a subnet argument, the caller is also implicitly providing an availability zone to use. To better illustrate the property of static stability, let's look at Amazon EC2, which is itself designed according to those principles. When building systems on top of availability zones, one lesson we have learned is to be ready for impairments before they happen. A less effective approach might be to deploy multiple availability zones with the expectation that should there be an impairment within one availability zone, the service will scale up, perhaps using AWS autoscaling, in other availability zones and be restored to full health. This approach is less effective because it relies on reacting to impairments as they happen, rather than being prepared for those impairments before they happen. In other words, it lacks static stability. In contrast, a more effective statically stable service would over-provision its infrastructure to the point where it would continue operating correctly without having to launch any new EC2 instances, even if an availability zone were to become impaired. The Amazon EC2 service consists of a control plane and a data plane. Control plane and data plane are terms of art from networking, but we use them all over the place in AWS. A control plane is the machinery involved in making changes to a system, adding resources, deleting resources, modifying resources, and getting those changes propagated to wherever they need to go to take effect. A data plane, in contrast, is the daily business of those resources, that is, what it takes for them to function. In Amazon EC2, the control plane is everything that happens when EC2 launches a new instance. The logic of the control plane pulls together everything needed for a new EC2 instance by performing numerous tasks. The following are a few examples. It finds physical server for the compute while respecting placement groups and VPC tenancy requirements. It allocates a network interface out of the VPC subnet. It prepares an EBS volume, generates IAM role credentials, installs security groups, stores the result in the data stores of the various downstream services, propagates the needed configurations to the server in the VPC and to the network edge. But in contrast, the Amazon EC2 data plane keeps existing EC2 instances humming along as expected, performing tasks such as routing packets according to VPC route tables, reading and writing from EBS volumes, and so on. As it's usually the case with data planes and control planes, the Amazon EC2 data plane is far simpler than the control plane. As a result of this relative simplicity, the EC2 data plane design targets a higher availability than that of the EC2 control plane. But, the concepts of control planes, data planes, and static stability are broadly applicable, even beyond Amazon EC2. Being able to decompose a system into its control plane and data plane can be a helpful conceptual tool for designing highly available services for a number of reasons. It's typical for the availability of the data plane to be even more critical to the success of customers than the control plane. For instance, the continued availability and correct functioning of an EC2 instance after it is running is even more important to most of you than the ability to launch a new EC2 instance. It's typical for the data plane to operate at a higher volume, often by orders of magnitude, than its control plane. And as it's better to keep them separate so that each can be scaled accordingly to its own relevant scaling dimensions. And we found that over the years, a system's control plane tends to have more moving parts than its data plane, so it's statistically more likely to become impaired for that reason alone. So putting those considerations all together, our best practice is to separate systems along the control plane and data plane boundary. To achieve this separation in practice, we apply principles of static stability. A data plane typically depends on data that arrives from the control plane. However, to achieve a higher availability target, the data plane maintains its existing state and continues working even in the face of a control plane impairment. The data plane might not get updates during the period of impairment, but everything that had been working before continues to work. Earlier, we noted that a scheme that requires the replacement of an EC2 instance in response to an availability zone impairment is a less effective approach. It's It's not because we won't be able to launch the new EC2 instance, it's because in response to an impairment, the system has to take an immediate dependency for the recovery path on the Amazon EC2 control plane, plus all of the application-specific systems that are necessary for a new instance to start performing useful work. Depending on the application, these dependencies could include steps such as downloading runtime configuration, registering the instance with discovery services, acquiring credentials, etc. The control plane systems are necessarily more complex than those in the data plane, and they have a greater chance of not behaving correctly when the overall system is impaired. Several AWS services are internally composed of a horizontally scalable, stateless fleet of EC2 instances, or Amazon Elastic Container Service, or ECS containers. We run these services in an auto-scaling group across 3 or more availability zones. Additionally, these services over-provision capacity so that even if an entire availability zone were impaired, the servers in the remaining availability zones could carry the load. For example, when you use 3 availability zones, we over-provision by 50%. Put another way, we over-provision such that each availability zone is operating at only 66% of the level for which we have load tested it. The most common example is a load-balanced HTTPS service. The following diagram shows a public-facing application load balancer providing an HTTPS service across 3 availability zones. The target of the load balancer is an auto-scaling group that spans the 3 availability zones in the EU West 1 region. This is an example of an active-active high availability using availability zones. In the event of an availability zone impairment, the architecture shown in the preceding diagram requires no action. The EC2 instances in the impaired availability zone will start failing health checks, and the application load balancer will shift traffic away from them. In fact, the Elastic Load Balancer service is designed according to this principle. It has provisioned enough load balancing capacity to withstand an availability zone impairment without needing to scale up. We also use this pattern even when there is no load balancer or HTTPS service. For instance, a fleet of EC2 instances that processes messages from an Amazon Simple Queue service or SQS can follow this pattern too. The instances are deployed in an auto-scaling group across multiple availability zones, appropriately over-provisioned. In the event of an impaired availability zone, the service does nothing. The impaired instances stop doing their work and others pick up the slack. Some services we built are stateful and require a single primary or leader node to coordinate the work. An example of this service is a relational database such as Amazon RDS with a MySQL or Postgres database engine. A typical high availability setup for this kind of relational database has a primary instance, which is the one which all writes must go to, and a standby candidate. We might also have additional read replicas, which are not shown in this diagram. When we work with stateful infrastructure like this, there will be a warm standby node in a different availability zone from that of the primary node. The following diagram shows an Amazon RDS database. When we provision a database with Amazon RDS, it requires a subnet group. A subnet group is a set of subnets spanning multiple availability zones into which the database instances will be provisioned. Amazon RDS puts the standby candidate in a different availability zone from the primary node. This is an example of active standby high availability using availability zones. As was the case with the stateless active-active example, when the availability zone with the primary node becomes impaired, the stateful service does nothing with the infrastructure. For services that use Amazon RDS, RDS will manage the failover and repoint the DNS name to the new primary in the working availability zone. This pattern also applies to other active standby setups, even if they do not use a relational database. In particular, we apply this to systems with a cluster architecture that has a leader node. We deploy these clusters across availability zones and elect the new leader node from a standby candidate instead of launching a replacement just in time. What these two patterns have in common is that both of them have already provisioned the capacity they need in the event of an availability zone impairment well in advance of any impairment. In neither of these cases is the service taking any deliberate control plane dependencies, such as provisioning new infrastructure or making modifications in response to an availability zone issue. This final section of the talk will go one level deeper into resilient availability zone architectures, covering some of the ways in which we follow the availability zone independence principle in Amazon EC2. Understanding some of these concepts is helpful when we build a service that not only needs to be highly available itself, but also needs to provide infrastructure on which others can be highly available. EC2, as a provider of low-level AWS infrastructure, is the infrastructure that applications can use to be highly available. There are times when other systems might wish to adopt that strategy as well. We follow the availability zone independence principle in EC2 in our deployment practices. In EC2, software is deployed to the physical servers hosting EC2 instances, edge devices, DNS resolvers, control plane components in the EC2 instance launch path, and many other components upon which EC2 instances depend. These deployments follow a zonal deployment calendar. This means that two availability zones in the same region will receive a given deployment on different days. Across AWS, we use a phased rollout of deployment. For instance, we follow the best practice, regardless of the type of service to which we deploy, of first deploying a one box and then one by N of servers, etc. However, in the specific case of services like those on Amazon EC2, our deployments go one step further and are deliberately aligned to availability zone boundary. That way, a problem with the deployment affects one availability zone and it's rollback and fixed. It doesn't affect any other availability zones which continue functioning as normal. Another way we use the principle of independent availability zones when we build in Amazon EC2 is to design all packet flows to stay within the availability zone rather than crossing boundaries. The second point, that network traffic is kept local to the availability zone, is worth exploring in more detail. An interesting illustration of how we think differently when building a regional, highly available system that is a consumer-independent availability zones. That is, it uses guarantees of availability zone independence as a foundation for building a high available service, as opposed to when we provide availability zone independent infrastructure to others that will allow them to use for high availability. The following diagram illustrates a highly available external service, shown in orange, that depends on another internal service, shown in green. A straightforward design treats both of these services as consumers of independent EC2 availability zones. Each of the orange and green services is fronted by an application load balancer, and each service has a well-provisioned fleet of backend hosts spread across 3 availability zones. One highly available regional service calls another highly available regional service. This is a simple design, and for many of the services we've built, it is a good design. But suppose, however, that the green service is a foundational service. That is, suppose it is intended not only to be highly available, but also itself to serve as a building block for providing availability zone independence. In that case, we might instead design it as 3 instances of a zone local service, on which we follow availability zone aware deployment practices. The following diagram illustrates the design in which a highly available regional service calls a highly available zonal service. The reasons why we design our building block services to be availability zone independent come down to simple arithmetic. Let's say an availability zone is impaired. For black and white failures, the application load balancer will automatically fail away from the affected nodes. However, not all failures are so obvious. There can be gray failures, such as bugs in the software, which the load balancer won't be able to see in its health checks and cleanly handle. In this example, where one highly available regional service calls another highly available regional service, if a request is sent through the system, then with some simplifying assumptions, the chance of the request avoiding the impaired availability zone is 2 divided by 3 times 2 divided by 3. So it's 4 divided by 9. That is, the request has worse than even odds of steering clear of the event. In contrast, if we build the green service to be a zonal service, as in the current example, then the hosts in the orange service can call the green endpoint in the same availability zone. So with this architecture, the chances of avoiding the impaired availability zone are only 2 divided by 3. If n services are a part of this call path, then these numbers generalize to 2 divided by 3 to the power of n for n regional services versus remain constant at 2 divided by 3 for n zonal services. It is for this region that we built Amazon EC2 NAT Gateway as a zonal service. So NAT Gateway is an Amazon EC2 feature that allows for outbound internet traffic from a private subnet and appears not as a regional VPC-wide gateway, but as a zonal resource that customers instantiate separately per availability zone, as shown on this diagram. The NAT Gateway sits in the path of the internet connectivity for the VPC and is therefore part of the data plane of any EC2 instance within that VPC. If there is a connectivity impairment in one availability zone, we want to keep that impairment inside that availability zone only, rather than spreading it to other zones. In the end, we want a customer who built an architecture similar to the one that we mentioned earlier, that is like providing a fleet across 3 availability zones with enough capacity in any 2 to carry the full load, to know that the other availability zones will be completely unaffected by anything going on the impaired availability zone. The only way for us to do this is to ensure that all foundational components, like the NAT gateway, really do stay within one availability zone. So some lessons learned. When designing a service-oriented architecture that will run on AWS, we have learned to use one of these patterns or a combination of both. The simpler pattern, regional calls regional. This is often the best choice for external-facing services and appropriate for most internal services as well. For instance, when building higher-level application services in AWS, such as Amazon API Gateway and AWS serverless technologies, we use this pattern to provide high availability even in the face of an availability zone impairment. The more complex patterns are regional call zonal or zonal call zonal. When designing internal and in some cases external data plane components within Amazon EC2, for instance, network appliance or other infrastructure that sits directly in the critical data path, we follow the pattern of availability zone independence and use instances that are siloed in availability zones, so that network traffic remains in its same availability zone. This pattern not only helps keep impairments isolated to an availability zone, but also has favorable network traffic cost characteristics in AWS. Thank you for listening to my talk, and I hope you find it useful. If this topic interests you, you can find more dive deep articles on the Amazon Builders library, which you can find in the public AWS website. Have a great day!